Quarantine period mathematics 3. In this video, the continuation of the previous two, I am going to give a simple example or a simple application of mathematics in programming. In computer programming, the efficiency of the program is measured in terms of the length of the program or the execution times, how much time it will take to give the output. So if the execution time is reduced, for example 50%, definitely it will be treated as a better program. So what you know in plus 2, that mathematics, I am not going to give much different or higher mathematics, very simple mathematics, that how it plays an important role in reducing the execution time. A simple example. Tamil medium students க்கும் இது புரியும். ஏன்னா நீங்க ரெண்டு தான் ஞாபகம் வச்சுக்கணும். பிரைம் நம்பர் அப்படின்னு நான் சொல்லணும்னா அது பகாயன், டிவைசர் வகுத்தி, இது உங்களுக்கு தெரியும். So prime number is a number which is divisible by 1 and itself. 1 is neither prime nor composite. 2 is the only even prime. 3, 5, 7, etc. it goes. So this is the concept. Nowadays, in computers, in the world of networking, the password protection is mainly based on very large prime number. That you will study in detail later. So, in order to identify whether it is a prime or not, for example 10,001. So, to check 10,001 is a prime or not necessarily plus 2 students who have taken computer science as a subject. Even for biology students, they can understand if you know the mathematics. So, how to identify 10,001 is a prime or not? You have to check 2 is a divisor, 3 is a divisor, 4 is a divisor or not. Like that, if you go up to 10,000, if none of them divides, you will declare that it is a prime number. But suppose if you reduce instead of 2 to 10,000, if it is 2 to 5,000, it is a better program. So the actual program is 2 to n minus 1. You have to check the divisor from 2 to n minus 1. But a better algorithm is from 2 to n by 2. 50% of the execution time is reduced. What is the mathematics in that? That only we are going to discuss. Comparatively a better algorithm is you can go up to root n. So I am going to give this mathematics in 2 or 3 slides in this presentation.
This is a C program where the loop continues from 2 to I minus 1 that you can see. This is a better algorithm where your loop is 2 to n by 2. That also you can see. So what is the mathematics in that?
So now we are mathematically going to justify why we can go up to n by 2, the prime number checking program. So I made it as a theorem. It's not available in the book, but for your reference I am giving this as a theorem. For every integer n, after n by 2, there is no proper divisor. For every integer n, after n by 2, there is no proper divisor. What do you mean by proper divisor? First, improper divisor. What do you mean by improper divisor? For n, for the integer n, 1 and n are improper divisors. Particularly for the number 6, 1 and 6 are improper divisors, but 3 is a proper divisor. Now you can understand. So after n by 2, there is no proper divisor, means there is only one divisor, that is n. So you can go up to n by 2, there is no need to go beyond the prime number divisor checking after n by 2. That's what this theorem says. To understand this, let us consider 2 examples. The divisor set of 18. So what is the divisor set of 18? 1, 2, 3, 6, 9, 18. You can check after 9. there is no proper divisor. Only 18 is the divisor. Next, the divisor set of 32. You have 1, 2, 4, 8, 16, 32. So after 16, there is no proper divisor. So definitely you can check up to the n by 2. That's what we want to say. That is the theorem, that is the mathematical justification. But the example cannot be a proof. So we need to prove in general. That is the analytical approach. So to prove this, let n be the given integer. We shall assume that let d be a divisor after n by 2. D is greater than n by 2. So d is greater than n by 2. That means that is just you can interchange 2 and n. 2 is greater than, d is greater than n by 2. That means 2 is greater than n by d. Just you can interchange these two because these two are positive numbers. You can interchange. So 2 is greater than n by d or n by d is less than 2. Right? N by d is less than 2. N by d is less than 2. But you can understand n by d is an integer, that is also a divisor. For example, for 18, if 6 is a divisor, 3 is also a divisor. 18 by 6. Correct? So for n, if d is a divisor, n by d is also a divisor, which is an integer. It is very, very essential to understand. Seems to be a fraction, but n by d, as d is a divisor, it is an integer. So n by d is less than 2, but n by d is an integer. So what it should be? It is nothing but 1. So n by d equal to 1, so d equal to n. So we have taken a divisor which is greater than n by 2 and we have proved that it is nothing but n. So after n by 2, there is no proper divisor. So you can go up to n by 2. That is what the mathematical justification in this case. Now, for a better programming, to check a given integer is a prime or not, in the previous slide we have discussed we can go up to n by 2, but even you can check up to square root of n. For example, for 10,001, the square root of 10,001 is 100 plus. So you can check up to 2 to 100, that is sufficient. So 10,000 times reduced to 5,000 times. Now it is only 100 times. How much time it is reduced? How mathematics plays an important role in this? What is the justification of this mathematics? The theorem says, if n has no proper divisor up to square root of n, then it is a prime. That is, if it is not having any proper divisor up to square root of n, then it is a prime. That itself, that is the theorem. So how to prove that? So given that n has no proper divisor up to square root of n, let us assume that we need to prove that it has no divisor after square root of n. Let d be a divisor which is greater than square root of n. Let us assume of n. Let d be a divisor of n which is greater than square root of n. D is greater than square root of n. So as d is a divisor of n, n by d equal to k is an integer. Definitely, already I told. If d is a divisor, the co-divisor is n by d. So n by d equal to k is a divisor of n. Now, k equal to n by d. So in the denominator d, we are going to put a lesser value than d. Since d is greater than square root of n, we are going to put instead of d square root of n. So what is the inequality? N by square root of n, that is less than n by square root of n. Inequality is an important subject in mathematics. So denominator value is decreased, so the total value is increased. So k is less than n by square root of n. What is n by square root of n? It is square root of n. So this equality is for the previous term, but k is less than square root of n. But k is an integer, which is a divisor. It is a contradiction. Contradiction to what? We have assumed that n has no proper divisor up to square root of n. But we have assumed that n has a divisor after square root of n. Because of that assumption, you get k equal to n by d is a divisor which is less than square root of n. It is a contradiction. Why this contradiction arises? Because we have assumed that there is a divisor after square root of n. So, if there is no divisor up to square root of n, definitely there will not be any divisor after square root of n. That is a beautiful mathematics you can understand. So, I have given a very simple mathematics what you know that plays an important role in computer science. So, I think you have understood what I told. We will see in the next video with some other concept. Thank you.